Hi everyone, welcome to Day 5, Section 3.4, Optimization with Linear Programming. Today we're going to learn about finding a maximum and minimum value of a feasible region, and we're also going to solve some real-world optimization problems using linear programming. Now, for the first idea, we're going to look at some of the basics. What is a feasible region and how do we find the maximum and minimum values? What you see in number 1 here is somebody who has already graphed a system of inequalities and shaded the solution region. That's what a feasible region is. All we're doing is we're looking at just the shaded solution region of a system of inequalities. So we can see that here. We can also see the vertices of that feasible region. If we are looking for the minimum and maximum values of a feasible region, what we need to do is we need to check the vertices. Because of all the solutions that occur in that shaded region, the minimum and the maximum value are going to occur at one of those vertices, not within the shaded area. So, in order for us to check those min and max values, we set up a table to organize our work. And in that table, we'll list the ordered pairs that are the vertices of the feasible region, and we'll take this objective function that they've provided with us, and we evaluate those vertices in that objective function. So my vertices, as I can see here, are at 0, 0. They're at 0, 6. They're at 5, 0. And there's another one at 2, 7. And as I plug in the x and y coordinates into the value of that objective function, 0 take away 0 gives 0. 0 take away 6 is negative 6. And 5 take away 0 is equal to 5. And finally we have 2 take away 7, and it's a negative 5. So as we check out those values, we have a minimum value at negative 6, and we have a maximum value at 5. So that's how we state our solution. The minimum for this feasible region is equal to negative 6, which occurred at the point 0, 6, and the maximum value of this feasible region is equal to 5, and that occurred at the point 5, 0. Right? And that's all there is to it. So now we take a look at the next example, and they haven't given us quite as much information here. You have to do the graphing yourself. They've given you a list, a system of inequalities, which is nothing more than what's called the constraints, and we need to graph the system ourselves and then determine the vertices so that we can check it into the objective function they've supplied. Alright, so let's go with our graphs here. We'll do the first line, a vertical solid line at x equals 0. That'll be red. And we're going to stay greater than 0, so we're going to go to the right there. The second line is going to be a horizontal line at 0, a solid horizontal line. We're going to be staying greater than 0 again, so this time we'll stay above the horizontal line. And finally, we have a line that will come here and we'll check out the x and the y intercepts. Throwing in a 0 for x, we'll get a 6 for y, and a 0 in for y, we'll get a 3 for x. So we'll be able to graph that line by connecting the x-intercept at 3, 0 and the y-intercept at 0, 6, again with a solid line. And now for shading here, as we check the function, 0, 0 is a solution, so we'll shade below there. Alright, so now as we look each of our shadings, we're staying to the right of the red, we're staying above the green, we're staying below the blue, so our feasible region is going to be a little triangle region here. And then we need to label the vertices of that region based on our graph. So we've got a point here, the y-intercept was at 0, 6. Our corner point right here is the origin at 0, 0. And our other x-intercept is one of the other vertices at 3, 0. So now I've got all the information I had in the first problem, and I can come back and set up my ordered pairs. I've got a new objective function to consider. I'm going to take 3x, take away y for each of those, and list my vertices. So I've got 0, 0. We're at 0, 6, and we're at 3, 0. And as I plug those in, 3 times 0, take away 0 is 0. 3 times 0, take away 6 is going to give a negative 6. And then 3 times 3 and take away 0 is going to give me 9. So again, checking out the values, I've got a minimum value at negative 6, I've got a maximum value at 9, and I can record my results here. So minimum at negative 6 and a maximum at 9. Alright, so now we know how to find the min or max of a feasible region, and we're going to apply that idea as we look at a real-world problem called linear programming. So turn the page over. Alright, so let's check out what we're doing here. Your class plans to raise money by selling t-shirts and caps. The plan is to buy the t-shirts for $8, sell them for $12, and to buy the caps for $4 and sell them for $7. The planning committee estimates that you will not sell more than 120 items. Your class can afford to spend as much as $800 to buy the articles. How many caps and t-shirt sales are needed to maximize your profit? So, as we were looking at the objective functions before, a lot of times these problems are about maximizing profit, and that's what's happening here. So before we can start writing equations or inequalities, we need to set up some variables. Alright, so we're selling t-shirts and caps. We're going to have one variable represent the number of our t-shirts, and we'll have the other variable y represent the number of caps that we're going to sell. Right. Now, the objective function is going to be about the objective of the problem. That last statement is telling you about your objective. You want to maximize your profit. So, we need to figure out profit for our t-shirts and our caps. Right. T-shirts we're selling for 8, we're buying them for 8 and selling them for 12. So the t-shirts are getting a profit of $4 each. The caps, we're buying them for 4 and selling them for 7. So the caps, we're going to be making a profit of $3 a piece. And that's what we put in this P equation, profit equation. We're going to be earning $4 per t-shirt, so 4 times X. And we're going to be earning $3 per cap, so 3 times Y. Alright, now that objective function, we won't be using it until we've graphed our feasible region and found the vertices. So we hold on to that for right now, and we have to go to a different part of it where we're writing our inequalities that we'll be graphing. And that's in part C, where we're going to be writing the constraints. So back to the problem where we can figure out how we're going to limit this function. Alright, now every linear programming problem has 2 basic inequalities. We can't sell a negative number of t-shirts or caps. So I can make 2 inequalities relating to that. X is going to be greater than or equal to 0. Y is going to be greater than or equal to 0. Basically, those 2 constraints are going to keep you in the first quadrant when you show your graph. The other 2, we're going to talk about, go back and look at the reading again. All right. The planning committee indicated that you won't sell more than 120 items. So, in terms of number of items, that's your t-shirts and the caps. So we're going to have one inequality that's going to say x plus y will stay less than or equal to 120. Right? And then we have another relationship that says, all right, you've got $800 that you can spend to buy the articles you need to sell. So, in terms of cost, the t-shirts are costing us $8 a piece, and the caps are costing us $4 a piece. So 8x plus 4y needs to stay less than or equal to that $800. All right. Now you have your constraints, and your job is to come and get the inequalities graphed, and also in the course of doing that to get yourself a scale for your axes and label your vertices. All right, so what we can do here below our 2 inequalities, since they're both in standard form, we can set up our x and y intercepts. So if I let x be 0 here, my y will be 120. If I let my y be 0, my x will be 120. So I have x and y intercepts for one graph. And then for the second graph, I'll do the same thing. If I let x be 0 here, the y value will be 200. And if I let y be 0, the x-intercept will be 100. All right, now we go down to the graph, and we're going to use those t-tables with our intercepts to get a nice sketch of our graph here. All right, units are 20 each on each axis, and the directions are, you've got to get your scale set up, and also you're going to label your axes for what they stand for. Once we get it graphed, we're also going to get our vertices of our feasible region. All right, so let's see. We have to go as far as 200 up on the y-axis. So let's see, then we're going to have these and go by tens, it looks like, probably. So this will be 200. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll be 100. So each little unit tick mark is 10. And then we'll keep that same scale on the x-axis. So we'll have a 200 here at the end. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll have 100. All right. X-axis we have labeled as number of t-shirts. And then the y-axis will be our number of our caps. All right, now plotting our points, we've got one graph here, and we're going to have a y-intercept at 120. Get that dot in there. And we'll also have an x-intercept at 120. All right, and we're going to connect that line as straight as we can. All right, and then the other line is going to have a y-intercept at 200, and it's going to have an x-intercept at 100. And we're going to draw and connect that line. All right, now we've also got our two inequalities at x greater than 0 and y greater than 0. And that's going to keep us our vertical lines and our horizontal line, and it's going to keep us in the first quadrant because we're going to be staying to the right of that vertical line and above the horizontal line. The two green lines we've graphed, they're both less than or equal to, and that means we're going to shade below them. So as we shade below both of them, the feasible region will be staying below that first graph till we get to this point of intersection, and then we're going to stay below there. All right. Now, of the corner points in our feasible region, a couple of them are just from our intercepts. So here we've got a corner point, a vertice of our region, and that's going to be at 0, 120. All right. The other one down here is going to be at the point 100, 0. And then, of course, we've got the origin is also 1. Now, the point right here, we might be able to read directly by our graph, but we also need to be sure we get it exact. So the safest thing to do there is to solve the system from those two equations that got graphed. So I'm going to come back up here to your inequalities, and I'm going to write the inequalities out here as though they were equations and solve that system so we get an accurate point there. So I've got an equation that said x plus y equals 120, and my other equation was 8x plus 4y equals 800. So elimination's a good method here. I'm going to get rid of the y's and multiply by a -4. So that'll give me a -4x, subtract 4y equals -480. And my y's are eliminated. I will end up with 4x equal to what? It will come out to be equal to 320. 320, and if I divide through by 4, I'll end up with 80. All right, plug that back into the first equation. 80 plus y equals 120, and I get my y equal to 40. And now I can say that I've got my last vertice point. I've got a point at 80, comma 40. All right, so now we've got everything we needed based on what we saw from the first two problems, and we're going to come over here and we're going to finish up the problem, which shows the last two pieces on the next page. Over here to the next page, let's make a table, and I'm going to take those vertice points that we just saw on the graph on the previous page, and I'm going to list them here. So my vertice points again, we're at 0, 120, and it was also at a point of 100, 0, and the point of intersection that we found was at 80, 40. And last but not least, we also had the origin in there. All right, now we come back to part B, where we had listed that objective function, that profit equation. And that profit equation had been 4x plus 3y. So we answered that back in part B. We're pulling it ahead now. This is the place where we need to evaluate it. So now we come back and we put each of our x and y values into our objective function. So 4 times 0, add 3 times y, we are going to get, what, 360? And we're going to throw a 100 in for x this time, 4 times 100, and 3 times 0. And that'll give us 400. And we're going to put in the 80, so we're going to have 4. We are going to have 4 times 80, and 3 times the 40. And that total is going to give us 440. And then, of course, if we put the 0 in, 4 times 0 and 3 times 0. You don't sell, you don't make money. There's a 0. All right. So we come back, and again, our objective was to make the most money, and that is going to occur right here. We can come here and we can explain what our table is showing here. We have, you will earn a maximum profit of $440 by selling, and this is where your ordered pair comes in important here. We got that profit with the ordered pair 80/40. So that means we're going to be selling 80 t-shirts, 80 t-shirts, and 40 caps. And there you go. Your summary of that solution should reflect your evaluating your ordered pairs in your feasible region, and also using that ordered pair value that obtained that one. So there you go. You've got your first chance at objective functions, and we're all set here. And that's it. Thanks. Bye now. Have a good night.